role of the heart is to pump nutrients and oxygen to the rest of the tissue. What's really important to remember is that the heart itself is an organ and a muscular tissue. Therefore, it needs to receive its own nutrients. Why can't the heart just take nutrients and oxygen and deposit carbon dioxide into the blood it receives into the atria? There are several reasons why this can't happen. The first is that the chambers are lined with a watertight endothelial lining. This doesn't allow blood to pass from the chamber into the muscular tissue. The second is that the ventricle and the heart tissue itself is too thick. We talked about how diffusion is limited by distance. If the blood was expected to diffuse from the atria all the way to the outermost tissue, this would take too long and the other tissues would likely die due to lack of oxygen or a low pH change. Therefore, the heart has its own circulatory system, similar to every other cell in the body. The green arrow indicates where the coronary circulation begins, just before the aortic arch and just after the semilunar valve. The coronary blood all ends up draining back into the right atria, so that blood again can be refreshed by going through the pulmonary system. The heart receives most of its blood flow during diastole. This is heart relaxation. There are a couple of reasons why blood flow is most prominent during diastole. The first is that as the cardiac tissue contracts, it forces the muscle to shorten, and therefore it compresses on the entire coronary blood flow system. The black arrows indicate when contraction occurs in the ventricle and the atrium, how the muscle tissue actually squeezes and compresses and makes the heart smaller. By making the heart smaller, it puts more pressure on the coronary vessels and actually can close those vessels or squeeze those vessels shut because the contraction force is so great. If we look at an isolated blood vessel down at the bottom of the whiteboard, and we think about what would happen if this received a squeezing force. So if all of a sudden I took my fist and squeezed on that blood vessel, what would end up happening is that blood vessel would narrow in that portion. And if contraction force is large enough, we could fully close that blood vessel. That's what happens during systole in the heart. As the muscles contract around the blood vessels, it narrows those blood vessels, and if that heart has to generate so much force to overcome the systolic pressure, those vessels can actually be closed completely momentarily while contraction occurs. The second reason why blood flow is typically given to the heart during diastole is the opening of that aortic valve. During systole, that aortic valve opens and the flap of it actually will close the entry into the coronary artery. So you can see as systole occurs, the aortic valve opens and that flap will actually come up and close entry into the coronary arteries. This prevents blood from entering into the heart and therefore prevents blood from reaching the cardiac tissue. Cardiac tissue predominantly relies on oxidative phosphorylation. This means it needs a very large supply of oxygen to supply its mitochondria with enough oxygen to generate ATP. In most cases, during rest and exercise, the heart receives enough blood flow to meet its demands. Problems result when there is either a high blood pressure in the patient or individual, or if one of the coronary arteries becomes blocked. If a coronary artery becomes blocked, the tissue that is further downstream is at risk for either becoming oxygen deficient or potentially dying due to the lack of nutrients. So if we pretend that there are two potential blockage points in this individual, blockage point A or blockage point B, if blockage point A occurred, you would see that the blood would be pooled up further upstream, and as a result, all of the cardiac tissue below that point would no longer be receiving blood flow. This would be a significant portion of the left ventricle. However, if blockage point B occurred, we would see that there's only a small amount of coronary circulation that is not receiving blood flow. Therefore, the individual with a blockage at point B would have a higher chance of survival and less cardiac tissue that would potentially be damaged. Coronary arteries do not have to become fully blocked. They could also become partially blocked. Any blockage or decrease in blood flow to the heart tissue is known as coronary artery disease. As metabolic demands increases, blood flow to the coronary arteries needs to increase as well, because the heart has to work harder to pump adequate amount of blood to the remainder of the tissue in the heart. There are 3 ways that coronary artery disease can lead to a possible heart attack. One would be by producing vascular spasms in the coronary arteries, the formation of a plaque within the arteries, and a thromboembolism. Vascular spasms is a way that we describe a narrowing of the coronary vessels. Vascular spasms are an early sign of coronary artery disease and are most often triggered by cold, physical exertion, or by emotional distress. Vascular spasms are caused when too little oxygen is available in the coronary vessels to meet the metabolic need of the cardiac muscle. This releases a platelet activating factor, which causes a vasoconstriction of the smooth muscle. Atherosclerosis is an actual buildup within the coronary artery or vein. This leads to a decreased flow because the pathway for blood to move through that artery is decreased. Atherosclerosis remains in place and is simply just a narrowing of that artery. There are several problems with developing an atherosclerosis plaque. The first is if we look on the left, during normal conditions, blood flow is at an optimal. It has blood that is able to flow through the entire vessel. As the plaque builds up, it decreases the amount of blood that can flow through that area because there is a decrease in radii. This causes less blood to be available for the tissue downstream and an increase in pressure build up in that tissue. The second issue relates to the ability of the cells in the surrounding area to perform diffusion with its concentration gradients. All of the red ovals on the outside of the artery represent cells. These cells need to be able to take in oxygen and put out carbon dioxide into the blood to maintain their ATP rate of production and maintain the cell's pH. As you can see, the plaque buildup is going to hinder the exchange with the cells to the right of the plaque because we have an increased distance for diffusion to occur in. Two further complications of developing atherosclerosis in a coronary artery is one, angina pectoralis, which is pain of the heart. This is really common in Minnesota after we get our first snowfall. All of a sudden, a man or woman who is relatively sedentary and doesn't have a high stress on their heart during normal everyday activity, all of a sudden goes outside to shovel snow. While they're shoveling snow, there is an increase in metabolic demand to the tissue in charge of lifting the snow and their legs through walking. To complicate matters further, it also places them in a cold condition where they are more susceptible for vascular spasms. This increase in metabolic demand, along with the potential for vascular spasms, can decrease oxygen received by the myocardial tissue. This becomes felt as a pain in the heart or the shoulder because of an inability for oxygen delivery to meet oxygen demand. As soon as physical activity decreases, the pain goes away. It will reoccur anytime high physical demand is placed back on the heart. And the greatest problem of atherosclerosis is the development of a thromboembolism. A thromboembolism would occur if that plaque, which is typically adhered to the vessel's lining, were to become unstable and break off. This would allow for the plaque to dislodge from the vessel and go further downstream where the vessels typically narrow in diameter. This can lead to a partial or full plugging of the vessel and decrease blood flow through the rest of the coronary circulation. When this vessel becomes completely plugged, a heart attack occurs and the tissue served by that vessel soon dies from being deprived oxygen. The extent of the damage, again, we said has to do with the location of the thromboembolism. If the embolism got blocked at part A, or blockage A, on the heart, it would have a greater or more significant effect because at that point, the blood still has to supply significantly more myocardial tissue than if it occurred at blockage B.